We'll be starting showing up on our screen. So this is the July to December schedule, and it will be shared in the chat box, and also it will be shared in the chat room on Telegram and on WhatsApp. So please, we all should endeavor to get familiar and get ready for the second half of the course. Also, we have a summer program going on, which is being displayed. It is Diploma in Artificial Intelligence and Machine Learning. It's actually kickstarted already, but we haven't gone too deep into it, and we all are endeavored. It is actually compulsory for us to register for this course and be present in class. So according to the curriculum highlights, you can see there we have AI Foundation, we have prompt fundamentals. We're going to teach you how to prompt your ChatGPT and every other AI tool you use. We have AI for various industries. We have AI for business functions. How are you going to improve your business using all these AI agents? Also, we are going to be building AI models like Zoo Creator and AI Modeler. Also, we are going to be going into Microsoft Copilot. How are you going to utilize Microsoft Copilot for your business, for your day-to-day life, for your work? So this is really, really, really important. This is the next level thing for us. Also, we're going to be learning Python fundamentals, TensorFlow, and PyTorch. Actually, we've gone a bit into that in the AI and automation class, this class. If you're joining for the first time, if you haven't been in our subsequent in our past classes, you can actually check our YouTube page and get on them. So we are all encouraged to register for this program. Also, the registration link will be posted in the chat box very soon. So without taking too much, we already have 8 minutes gone in, and we have enough people in class. So we'll be inviting our trainer for today, Mr. Obinna Onwuka. So while we share the links for the registration and also the schedule for the second half of the year, we're going to put our hands together for Mr. Obinna in the chat box as he takes over. Mr. Obinna, are you there with us?
Good morning, everyone. Please, I don't know if my voice is quite audible. Please, can anyone confirm if my voice is audible enough for this meeting?
Yes, we can hear you, Mr. Obinna.
So, naturally, I should tell you that we'll be talking about semantic segmentations and maybe object detections, and also go to the unit part. And to an extent, even for an AI engineer, it might be a bit complicating for an AI engineer. So there are normally prerequisites to these particular topics. Like there are things you need to know or things you need to be conversant with before you actually do this kind of topics. And at least to an extent, I'll say, since we've been doing these classes, I should assume that maybe I don't need to say much for like us to like get back to like understanding this particular topic I'll be taking. So I'll be asking some questions, and I don't know, maybe based on your questions, I should be able to know how to attend to us. So please, maybe in the chat box, you can answer me, or in the chat room, you can answer me. Like when it comes to this particular topic, now we'll be going through like deep learning, we'll be going through CNNs and perceptrons. So does anyone here know about what I just listed now? Like, do you have a clue about deep learning, CNN, perceptron? Like, let's start with these three. Does anyone understand the concepts behind these three stuffs I just called?
Sorry, Mr. Obinna, if you would want to speak, you are able to unmute your mic. Please go ahead. You can unmute your mic and interact with the trainer.
Okay, yes, that's better. Hello, is anyone here with me?
Please, Mr. Obinna, please go ahead and ask the question again. I can see some people leaving and joining back. I guess they had internet issues.
Okay, so we'll be talking about object detection, semantic segmentation, and the unit aspects of deep learning with respect to artificial intelligence. And like I said earlier, does anyone understand the prerequisites? Like, do you know about Python? Do you know about CNN? Do you know about perceptrons? Do you know about deep learning? Like, do you have an idea about what these particular things I just called? Do you have an idea about them? So I know how to like forge ahead with this meeting. You don't need to like type it out. You can, or maybe if you're too shy, you can type it out.
Yes, good afternoon, sir.
Good afternoon.
Yeah, my name is John.
Welcome, John.
Can you hear me, sir?
I can hear you. I can hear you.
Yes, I have basic knowledge of Python. That's what we've been using since our previous classes, and just have a basic knowledge of deep learning. That is a subset of machine learning that can be used in image recognition and other things, other complex data trainings.
Okay. Okay. Thank you very much, Mr. John. Okay, so I guess maybe the reason the others have not said anything is because of they don't maybe understand it, or are they embarrassed to just well okay, so I guess maybe we'll just start from the prerequisites, and because I like the people I work
Hello,
with to be
good
carried
morning.
along. Okay, good morning. Good morning.
Yes, I don't know if my opinion would represent the opinion of most of us who are not also responding. I don't know anything about it, so that's just for me anyway. Thank you. So I will appreciate, like you are saying, to go very basic.
Okay, no problem, Mr. Oluwatobi. Okay, so let me see your answer. Like, it's okay to answer for everyone. So I will have to go maybe back to the CNN because I really want everyone being carried along. I just don't like talking, and it's more like I'm talking to myself whenever I'm teaching. I like the people I'm teaching to understand that, okay, in as much as I'm saying something, they can always relate to terms I use. So, okay, we'll be so let's go back to the CNN. So I'll be sharing my screen now because I had to like get a particular note we have to like scan through, and I'll try make sure that everyone understands this particular thing. I'll try use relatable words. I'll try make sure that it's not just ambiguous textbook definition. It's always going to be something that, well, you look around and you maybe tend to maybe liaise with whatever AI or CNN or RNN or the rest is. So let me just share my screen just a minute. Okay. Okay, please, can you confirm if my screen is like, can see my screen?
Yes, you can see your screen.
Okay, so this class will be ending around 1, so I understand we have a lot to like talk about. So but if at any point you're not carried along, please let me know so that I come back to the part and answer any question. And at any point where you feel maybe you need more clarifications on a particular thing, just let me know. And I'll be there to just maybe answer your question as comprehensively as possible. Okay, so okay, we have AI, we have ML, we have DL, which is the deep learning, and we have data science. Now, at some point, okay, when I was like starting my data journey, I had to start with data analysis. And well, I'm sure most of us know what data analysis is about, trying to like get your data and try to make sure you clean your data and the rest, and make sure that your data presentable for your stakeholders, and then your stakeholders get to, like, you give them a very, because we have the soft skill and we have the analytic skill. So in as much as you're done getting a very, very good data from your raw or your previous data, the best way for you to sell whatever is via data visualization. And then your stakeholders need to understand what you did, and then maybe it's going to also solve a problem. So data is very, very wide, and just like we are now, the oil is data, just like they said. So I'll be talking about how they are connected in a way. I'll be talking about AI, ML, DL, which is deep learning, and data science. Now, just like you said, Mr. Oluwatu, data deep learning is actually more like, should I say, it's a subset of artificial intelligence. Now, the sweet part about deep learning is, just like I said, I'll be using human analogies to explain this particular thing. Now, we have machines at this particular moment trying to mimic the human mind, trying to mimic the human thoughts. And that's one beauty, because just like we are seeing our airplanes, the Wright brothers actually mimicked the birds. So when it comes to creativity, it's actually best when you try to mimic something so natural to create something in a way artificial. And that's where deep learning comes in, because if deep learning is actually mimicking the human brains, then it has to work with a lot of neurons. It has to work with artificial neural networks. It has to work with perceptrons and the rest. So I'll explain the perceptron in a minute. But the idea behind it is it's trying to just mimic the human brain, how the brain thinks, how the brain is able to see something and then process that information and then be able to like understand it in case it sees it the next time. So if you can remember, maybe at some point you did your machine learning, you did your trainings and you trained your data. Now, the beauty about the deep learning here is it's actually looking at things around you. Your brain now is processing it. The neurons in your brain is processing the information you're seeing, and the information you are seeing is actually data. So it's processing it, and then your brain, based on previous reinforced learnings, because when a kid is small, it has to like watch its parents, how they talk, for it to be able to start saying dada or mama. And maybe some mothers now, they actually want their kids to say mama before dada first. So the mother now, why spending more time with the kid, will actually say mama, 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 but unfortunately the kid will betray the mother and say dada, because of, in a way, like what the mommy is doing is trying to like, she's trying to reinforce that kid, like something they call reinforced learning. You're trying to show a particular model something continuously, so that when it sees it or when it like comes in contact with that particular thing, it's like understands it so well. So that's the idea behind deep learning. It mimics the human brain. So please, just like I said, if you don't really understand what I'm saying, just let me know, and I'll come back to what you like need to understand. So I won't go into the machine learning. Like I'm sure maybe you understand the machine learning and the data science. Now, data science is more like it's all encompassing. It's like if you're actually doing I, we did artificial intelligence, we did machine learning, which is very, very necessary. And we also did deep learning. So data science is actually covering a lot of these things. So, okay, but well, we're talking about the deep learning. So, but if at any point you need special clarifications on AI, ML, DL, and TS, please let me know. And then if I should also say something again, like I don't know, maybe if you check your algorithms on Twitter or on social media, there's something about like, have you noticed that when you do something on, or you search something on Google and you go to YouTube, in a way, YouTube, you did not search the thing on YouTube, you search something on Google. But when you come to YouTube, you start seeing things, videos that are similar to what you just searched. That's one thing about artificial intelligence. That's one thing about deep learning. Now, the way or the like, if I should use a particular data deep learning expression to like justify that. It's called cosine similarities because it looks at the similar things that you search and then it creates an algorithm to favor such search. Just like I'm not sure there are some things that naturally will come into my data feed. The things that should naturally come to my data feed are things that I maybe searched at some point, or the things I actually liked, or the things I clicked. And that's the beauty because now your software is actually mimicking the human brain because unlike poles, like birds of a feather, they flock together. So in a way, if you don't really want something, you don't get it. So when you see an algorithm, you should understand that maybe the algorithm is actually coming based on what you saw initially or what you liked or what you searched or something is going on at the moment, which I should say, or what you say too, meaning that it has been said that our phone has the ability to record keywords. And then when you say those things, you can go to YouTube and funny enough, you will see those things. I remember I was talking about Steph Curry, comparing Steph Curry and LeBron James. And I was saying I prefer Steph Curry to LeBron James. And I am not lying. I went to YouTube, I went to Twitter, and I saw best 3 pointers of I'm like, what is this? Like, am I being monitored? So that's the beauty, and or I would say maybe one of the disadvantages of deep learning or artificial intelligence. It mimics the human brain, tries to get us what we want without us asking. And the process of doing that is what like they call cosine similarities, or you can use Euclidean distance, but well, we'll get to that part. So okay, so now let's talk about the perceptron here. Let's talk about the perceptron. Now, before, please, can you confirm if you're still seeing my screen? Because I don't just want to talk and then it's more like I'm talking to myself.
Yes, you
I'm
can
the
see
only
it, sir.
one. Okay, thank you. So,
I can see it, sir.
okay, thank you very much. Okay, thank you. So now we'll talk about the perceptron now. Now, the perceptron normally is like a foundational building block of neural network and deep learning. Like what this perceptron is centered on is it's trying to mimic a biological processing input, like to process output. So the idea behind this now, let me use a particular term. I know we are seeing study, play, and sleep here, and just like a machine learning data set, naturally you're going to give it an input, and then the input you have to like have a dependent input and an independent output. So the idea there is it's going to use your dependent input to like it's going to train it, and then from there it's going to get your independent output. That's brilliant for machine learning. It uses past data that we used in training our models to predict future occurrence, giving it an accuracy, or maybe that's nice, giving an accuracy, precision, that's cool. But here we're talking about perceptron now. A perceptron, what perceptron will naturally do? Let me use our human analogy now. Let's talk about perceptron. First of all, we have, sorry, please, can you like see the way I'm moving my mouse? Because I don't know if maybe, because I'm trying to use my mouse to get, can you see the way I'm moving my mouse, please?
Yes, we can see it.
Okay, thank you. Okay, so now we have the inputs here. We have the inputs here. And I want us to like link this input to our sense organs, our sense.
We can hear you, Mr. Obinna. Are you there? Mr. Obinna, okay, I guess his network glitch. Please let's give him a moment to
Oh God, oh God, oh God. Can
yeah,
you hear
back
me
with
now?
yes, we can hear you now.
Sorry for the break in transmission. Okay, so just like I said, with respect to this perceptron, we have
Mr. Obinna, your network is still having issues. We cannot hear you right now. Please, we are so sorry for the break in transmission. Please, let's give Mr. Obinna a few minutes to get his network back and join us. Thank you. So right before we get him back, please let's all check the chat box. I shared the registration link to the summer AI program, and also the attendance link has also been shared. Please let's all do well to fill in the attendance and also register for this AI summer program. It's really, really a great one. Please let's wait a moment while we let Mr. Obinna figure out his network and join back the call. Please, we are so sorry. We all know the network issue in this side of the world. So please, let's give him a moment to join back on the call. Oh, all right, Suzanne, I'll repost the registration link and the attendance right now. Thank you. All right, he's trying to join back. Let's all exercise a little more patience. All right, we have him back on the call, so he's going to be joining us right now. Mr. Obinna, are you there?
Yes, please, am I audible?
Yes, we can hear you now. Please, you can go ahead to share your screen.
Okay, I don't know. I'm so sorry. The network turned out bad, but Hopefully it doesn't happen again. I'll be sharing my screen now. Okay. 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 So the host can't disable screen sharing. So, and something been done on that.
Oh yes, you are make co-host now. Please go ahead.
Okay, thank you. Okay. Okay, so I said earlier that this perceptron now has the input, it has the hidden layer, it has the output layer, and it has the output. It also has something they call weights. It has bias and activation energy. But I just want to go one step at a time, so I don't like. So now for the input, now I want to maybe link it with our sense organs like the eyes for seeing, the nose for breathing, the skin for feeling, the mouth or the tongue for talking and tasting and stuff like that. Let's say now these particular entries are more like the input entries. Now, what this thing does, it's actually like gets a lot of data. Like it's like the eye now sees, and then when your eye sees and your brain is able to process those particular things, whenever you see something like that, you're going to like understand it without someone having to like tell you or train you again to understand it. So let's maybe use our body structure as the input systems now. And then now we also have something they call it. So I'm trying to explain these concepts. I'm trying to explain this concept so that at least everyone understands these particular things. So for the weight now, the weight is more like now for our bodies now, we understand that even though it's not fair, but to an extent, your you won't allow someone's hand get so close to your eyes, but you will allow someone get like you allow that same hand to get close to your skin, meaning that we understand that well we give more preferential treatments to the eyes compared to the skin. So now for the weight, now the weight is just like that. The weight is more like the preferential treatment we give to a particular input system, like a particular input. So weight means that the level of importance you're giving to a particular input, if I should use that particular term. Okay, and so we'll also talk about the bias. Now, one thing about this perceptron is, just like I said earlier, these sense organs, now what they do is they accept information, they process information. Now we have this particular round object here. And this round object contains our bias, it contains like the accumulation of like, okay, now for this X1 and W1, naturally for it to process what it's going to process, it has to like, you have to sum them up together. So we're going to have like the summation of X1 and W1 for us to like get this particular level of activation energy. But let me explain something now. Now, if maybe your skin now as the sense organ, you use like a hot object. Now, let's say maybe like you're cooking something and the thing gets to 100 degrees Celsius. And then maybe at some point, you need to get it down so it doesn't get burnt. Now you touch that particular thing and it's so hot that your brain naturally processes that you should take your hand away from that thing and or maybe drop whatever you're holding because it's so hot. Like so that's the idea behind this X1, which is more like the input. The X1 and the W1, for it to activate a level enough for the activation energy to come up, then naturally the energy should, like let's use the heat energy now. The energy, the activation energy now is what is like the heat is producing. Now for you to react, it means that the activation energy, which is the heat, has to be more than your input and your weight. That's the only thing that will make you react, because if the heat is not as much to cause any damage on your skin, you will naturally not drop the pot or the kettle. So the only reason why you're jumping after touching that particular thing is because of the activation energy. The activation energy has been surpassed by the input and the weight. So that's how maybe when we see a particular stuff, for us to process it continuously, it means that the input we're actually seeing is now surpassing the activation energy, and then from there we'll be able to process it to other parts of our body, like this particular one, to the other parts of our perception. So that's the whole idea. Now, the idea behind this bias now is, even if our brain, because naturally now at some point, based on we're not getting any input, our body will naturally base, okay, let's say we can get so reluctant with doing a particular thing, we might not want to react. So now the bias here is telling us that, okay, even if you don't want to react, even whatever you're processing into your brain is becoming zero, is negligent, is not is inactive or passive. Me, in my own capacity, I'll create a bias that will turn it to one. So that even if you're lying down on your bed and you don't want to even think of anything, your eyes will naturally look at something that will want to like process into your brain. Like you could be lying down and not doing anything, and whatever you're passing between your input and your weight is zero. But because of your brain naturally has to process something, the bias there will just turn that zero to one. And that one will be enough to overcome any activation energy for it to process the output. So please, just like I said, if you don't understand, please let me know so that I explain this thing more. So remember that even if you're lying down, you're dormant, you're really not doing anything, as long as maybe one of your body system or your sense organ is on, which is more like the input, or maybe you're lying down on the bed and then unfortunately you get a mosquito bite, you will naturally stand up and try to tap yourself. Or so that's the beauty about bias, because even if you don't want to do anything, the bias will naturally increase your zeros to one for it to pass to the output side. Now that we've passed through this activation energy side, now we're going to the output layer. Now for this output layer, now the output layer is one like, okay, now we've been able to process whatever we're processing. Now our output layer now is able to like get us the natural things that we should, okay, whatever passes through the like whatever passes through this center stage has gotten to the output layer. So the output layer is more like, okay, let's say if I was training a particular data set, now naturally based on our classifications, if we're having a binary classification, which is a Boolean thing, more like true or false, or ones and zeros in our binary classification. So our output layer now, because our bias has turned at any point, our bias has turned at any point where we are dormant, like a dormant zero, our bias has turned it to one. So now our output layer now is now one, meaning that, okay, now there's something to process. So now it has moved from this particular one now. Now the beauty behind perception here is that even though we have our wants, there's always an actual output and a predicted output. There's always an actual output and a predicted output. Now, for us that have been doing machine learning at some point, we understand that in as much as we're training our data, our predictions might not actually be 100%. And if our predictions are 100%, we'll be scared. We want to check whether there's an overfitting problem or there's something, or maybe we need to maybe check our correlation level. We need to check our confusion matches and the rest. So there's no certainty that whatever we're doing is going to be 100%. And that's the beauty, because of now that we know that there could be a deviation between the actual output and the predicted output. So now, then we'll now have our loss function, which is like in this final phase, which is this y with a cap there. This y with a cap is also called loss function. And the idea behind this loss function, it is the difference between the actual value and the predicted value. So that's the idea behind the loss function. Now, one thing about our perceptron here is if we are like passing, okay, now all these things I said, from the input to the weight, and then to the bias, and then to the activation energy, and then to the output layer, and then to the loss function, all these things, like I'm just going through a forward line, more like all these things I just said in sequence, they are what we call forward propagation, meaning that naturally, like if we should actually see something and follow it, more like a domino effect, like we have to start from a particular one to get to the other one, to get to the other one, then it's more like in perceptron, it's called forward propagation, meaning that our propagation is following a forward pattern from the input to the loss function. Now, it's not enough that will just end in loss function, because if we have an error, meaning the loss function, meaning there's a deviation between the actual output and the predicted output, it means that we have to also like go back to the source, try to understand or try to like train our data in a way that, okay, we make it understand or get better with time. It's just like if we tell our kid now, dada or mama, our kid will naturally not understand it at first. What our kid will do is it will be processing it. So the first time you're telling your kid, it's a forward propagation. You're telling your kid that, okay, say dada or don't say mama, say dada, and then your mama is saying, say mama, don't say dada. You guys are doing a forward propagation. And then the beauty here is your kid will naturally not understand, because if you tell your kid to say dada first time and your kid says dada, you might get scared and drop that kid and run away. So in a way to not get scared, your kid will naturally process this information. It will keep processing the information, and then for it to like get so well with this information, then we have to run a back propagation, meaning that it has to go front and back, front and back, front and back. It means that you're telling your kid to say dada, your kid is processing with all the whole hidden layers, with all the whole things in the perceptron, and then after your kid is processing it, then you have to like go back again and say dada, because the kid will be like, okay, he wants to hear you say it again. Okay, say it again, and then you have to say dada or mama, and then your kid will be like, okay, hear it continuously. So there's a forward propagation and there's a back propagation. Now, for this back propagation now, that is where we have our activation energy. That is where we have our optimizer. Now, the idea behind this optimizer here is it has to make sure that each and every weight we get updated, meaning that what we have or what we had in our loss function is updated when we're moving back to the input. So when we're running our back propagation, we are now talking about optimizers, and also aside optimizers, we're also talking about weight updating. We'll also go back to that side, but the idea behind this is like, okay, we have to go through our forward propagation, and then we'll have to come back to the back propagation. And for the back propagation, now we have our optimizer, which is naturally going to make sure that every weight that we've actually done earlier, we need to be updated while we are doing our propagation. And the reason why we need to do this is to minimize this loss in the place of loss function. Because of the beauty behind this is making sure that the difference behind the predicted one and the actual one is not like so wide. So that's why we have to actually run this particular thing. So, okay, so I'll just maybe slide through. Now, I also use another term. I'm sorry I have to like go through this particular phase, but I really want you guys to understand these basics, so that at least to an extent, whenever you're coming up with any term, like even if it's like the ones in code, you just know how to like relate to this particular thing. At least when you understand how to work, then you'll be able to know how to even fly, hopefully with time. So that's the beauty about these foundational phases. And then this gradient descent now. This gradient descent, for those that did machine learning in our linear progression, I'm sure at some point we must have gone through this gradient descent. Now, the gradient descent, the idea behind the gradient descent, I won't go deep into it, but I'll just try to say the right way so that at least we get to understand this point. Now, the gradient descent, now there's something they call slope in the gradient descent. There's something they call learning rate in the gradient descent. And naturally, the idea behind the gradient descent is we're trying to train our data so that it gets to the global minimal, like it gets to the global minimal, meaning that this our loss function now, when we want to train it, the idea behind minimizing the cost is so that it gets to the global minimal. And that's why we have these two parts here in our left-hand side and in our right-hand side. Now, the idea, like I said again, is to get to the global minimum, meaning that we have to keep training it. And by training it, it means that we have to work on our slope. We also have to work on our learning rates. We'll see it when we go down. But the whole concept is while we're running a forward propagation and a back propagation, it's in a way training our graded systems to just go gently to the part where it gets to the global minimum. And one thing about this thing is if our learning rate is too high, it overshoots the minimum. But if it is too low, then it slows convergence. The convergence meaning that convergence will only happen when we get to the global minimum. So that's the idea behind this loss function becoming so like infinitesimal if it's possible. So because the more we have more accuracy, the more our data will be actually like the more our data will be. Let me just say anything like the more our data will solve problem, the more our data will be reliable. So the more our models will be reliable. So um, there's nothing much to say here. We've talked about the input layers, the weights, the biases, the activation function, the loss function, which is the difference between the actual and predicted values. And we've also talked about the optimizer. Now, at some point, well, we'll also go to the part where I have to tell you that the optimizer is we have different types of optimizer. We have the Sigma optimizer. We have the stochastic gradient optimizer. We have the Adams optimizer. So we'll get to that part. And the idea behind this particular optimizer is so that we update our weight. So if you see the updated weight here, it means that the optimizer is truly doing the job. And why are we updating the weight? We're updating this weight in order to minimize the loss in our loss function. So I'll just go through this. And please, also, can you confirm if you're still seeing my screen and maybe if I'm audible, please?
Yes, we can see your screen and you're audible.
Okay, thank you very much. So I will not want us to go through all these rigmaroles and stuffs like that, but the whole idea is based on what I said earlier. This is just like a continuation of what I said earlier. And then, well, when it comes to the weight updating, there are terms that we'll naturally use. We'll have to use like maybe the weight updating formula. We have to use the chain rule of differentiation. Now, I don't know. I'll ask this question and I just want to understand if because there are real prerequisites to like being AI proficient. And I understand your test for knowledge and you trying to get better, building on solid foundation. Because when I see people embrace AI without understanding the concepts, whereas they always call themselves an AI enthusiast, I'm like, do you understand what you're talking about, AI? Because first of all, that you're proficient at giving a DeepSeek or ChatGPT good prompts doesn't make you any AI enthusiast. You have to understand the concepts at the back end for you to understand or for you to call yourself an AI enthusiast or maybe a prospective AI engineer. So there are prerequisites to this particular thing. And before we end this particular call, I'll try to maybe give you the things you have to know. The things you have to know, because if I should start talking about this weight updating formula now, or maybe the chain rule of differentiation, we'll have to now go back to statistics. And statistics is so broad because in statistics, we have to talk about probability, we have to talk about Pearson's law of correlation, we have to talk about a lot of things, the p-values and the rest. So I understand that time is not really our friend, there's a constraint to time, and so it's actually limiting a lot of things we need to do. But I also want you to know that there are things that you have to learn for you to get. And the beauty about AI is it's so understandable. You don't need to be tech savvy for you to understand. Well, you need to be tech savvy for you to understand this part, but you don't need to be like Albert Einstein or whatever for you to understand. You just have to like love what you're doing. So we'll go to that part later. So when it comes to like this back propagation now, we'll go through the stage of weight updating formula and the chain rule of differentiation. And the chain rule of differentiation is beautiful because of when I was doing this particular statistics at some point in my life, I actually loved it. Maybe because of it's like relates to statistics. Like I studied electrical engineering, so statistics was more like I could prefer statistics to writing letters. Though after school, I loved writing articles compared to statistics. But to an extent, we preferred calculating rather than like maybe talking. So the beauty there was like when I saw this weight updating formula, I was like, wow, this is nice. So at least at some point, when someone said, how many of you have used Pythagoras theorem to make money since you left school? That kind of stuff. And they will end it up with school na scam, school na scam. So when I saw my chain rule of differentiation, I was like, and I saw my statistics with respect to AI, I just said, wow, thank God, at least I can use my statistics knowledge now to at least make money. So that's the beauty. There's nothing you learn that is actually a waste. So like when I started the statistics and the chain rule of differentiation, this particular one is easy compared to the ones we did in advanced engineering mathematics. But the idea is it was so easy to know, like to solve those particular things. So in a way, whatever you're learning now is no waste. I'm sure at some point in your life you will always need it. You will always need it. And by the way, I've used Pythagoras theorem to make money too. So people are just saying nonsense, but you won't blame them. You just ignore their ignorance. So we'll be talking about the weight updating formula, and we'll also be talking about the chain rule of differentiation. Now, well, these are the formulas, and the weight updating formula is the idea behind this, because I won't go deep into it, but the idea behind this is when we have our, like I said, our gradient descent now, when we have our, when we have our, what's the word? When we have our inputs in the negative side of the slope, then there's a possibility that our new weight now that we're updating back to the input is going to be bigger. Sorry, our old weight. Sorry, our new weight, not old weight. Our new weight will be bigger than the old weight if our input, our input was found on the negative slope of our gradient descent. Now, how do I mean? In this formula that is here, we're seeing a minus here, and we're also seeing this particular thing that is in a rectangle. So now, if we have our negative here, and this thing is in a negative slope, it means that we have our learning rate and we have our slope here. So it means that our negative, we multiply the negative in this formula, and then it will get you the positive. And then our new weight, because after it gets us the positive, we'll add the summation to the old weight. It means that it's going to be way bigger than the new, like our new weight now will be bigger than the old weight. So it means that if we have our input on the negative side of the slope, our new weight will be bigger than the old weight. But if we have it on the positive, our old weight will be bigger. So the idea behind this gradient descent is to make sure that if we are on the negative slope, we should try to make sure that we introduce the positive, we introduce the positive value so that we can get convergence in the global minimum, meaning that we're reducing our loss function, thereby getting accurate predictions. And then if we're in the positive side, we need to make sure that we are reducing with our learning rates now. We need, please remember, this is the learning rate. So we need to make sure that we are introducing negative values to our input so that we can get convergence and then meet as our global minimum. So that's one of the beauties about weight updating. Remember, I said when we have our loss function and we have to do our backpropagation to go back to our input, then we need to update the weight. So this is the formula behind updating the weight. But the good thing again is you don't have to go through all these formulas when you're writing your codes, but it's best when you understand what you are writing, like the codes you're writing before writing them. Okay, and then our chain rule of differentiation. Our chain rule of differentiation is here. And well, the beauty behind this chain rule of differentiation is, I won't go into the nitty-gritties of this differentiation, but the formula here is okay, let me use a particular term now. If I want to get the chain rule of differentiation for the weight, like this W4 now, then I need to understand that W4 is dependent on W1 and is also dependent on the first input, which is input 1. So W4 now is dependent on W1 and is also dependent on X1, meaning that if I want to do my chain rule of differentiation, then I will expand it in the way that it's going to like consign the others, which is W1 and your X1. So in a way, this particular chain rule of differentiation is just like an extended version of okay, now let's use this particular, it's more like an extended version of our particular perceptron, linking all the whole inputs and weights together that are connected to themselves or that are dependent on themselves. So just like I said, okay, now let's use this particular term now. Now we're working on the W1 that is right here. Now, based on our formula earlier, we have change in loss, which is this part, it's here actually. Our change, our difference, we're differentiating the loss now because we're talking about the chain rule of differentiation. We're differentiating the loss, and then we're also, it's all over the differentiation of the output of 3,1 that is here, plus, so it's going to link it to this upper one up to this particular side. So it's going to link this particular up to this particular side, and it's also going to do this particular side up to this particular side. I understand this could be confusing. There was a time I did a combinational circuit and sequential circuit in this transformational college for some other students. So the beauty here is, I'm sorry I'm using the logical terms, but when it comes to circuits or perceptron, they are always connected to themselves. Like a node is connected to maybe another node, as long as, like if you're passing energy now, as long as you did not ground it, or maybe there are no insulations to maybe disrupt the passage of current, then your inputs and your outputs and anything between the input and your output will be so connected to the next, because of if you have your output and your input and maybe you cut one of the places between the input and the output, then you're not getting any result. So the beauty here is when we're working on our chain rule of differentiation, and maybe we're trying to update our weight one, we need to understand that starting from the loss function, we have to connect all these things together. And that's what we have here. We'll connect all these ones together. We'll also say, okay, now, even though we've connected the one at the top, well, we also need to connect the one at the bottom too. So that's the beauty behind our back propagation. So for our back propagation, we have the weight updating and we have the chain rule of differentiation. So I won't go into all this part because it's more like still the same thing we're talking about. And we'll also talk about, well, the activation functions too. Like we'll also talk about it. Just like I said, okay, maybe I did not say it, but we have sigmund, we have tan H, we have the ReLU, which is the rectified linear unit. We have the leaky ReLU and we have the pre-LU. We also have the LU, which is the exponential linear unit. So we'll get to that part when we see our codes. So there's nothing much to say. These sites are just for the loss functions too. Like for this loss function now, the loss function is also sharing the same formula as our mean square error. If we remember our mean square error in machine learning in linear progression, they will be able to understand this particular term, which is the loss function. It's so correlated with the linear progression and mean square error. So that's the whole formula here. And so maybe upon your request, I'll send these particular ones to you if you so need it. So for this particular mean square error, the mean absolute error, it's about the let's say the regressions. Now, if for the classifications now, our loss function for the classification, we also have other attributes to it, other loss functions to it. But based on the time that we don't have and me trying to make sure we cover a lot, I'll just go to the rest. But let me reiterate. For our binary loss function, we have, like when it comes to for our binary loss function, when it comes to our activation energy, we use the ReLU or we use the sigmund. When it comes to the categorical one, then we use the ReLU or the softmax, but we'll also get to that particular one very soon. And then when it comes to the optimizers here, so just a minute. When it comes to the optimizer, then what we're going to use is, like I said, we'll use our Adam for the optimizing. And please remember that our optimizer, the reason for optimizer is to make sure that we update our weight. And why are we updating our weight? We're updating our weight to minimize error based on what we have on the based on what we have on the perceptron. So, and what is a perceptron? A perceptron, like I said earlier, is just like a foundational building block of neural network. It's just like we have perceptron in our brain now. So the idea behind perceptron is just to mimic a biological neuron by processing inputs to produce output. So where we're going to get most of this particular one. Now, for this particular one now, this is more like the neuron here. And what is this particular thing doing here? It is pre-processing data. It is pre-processing data. And what is the meaning of pre-processing data? It means that whatever we're taking as input, it is the neuron which comprises of our activation energy, our bias, and the summation of the weight and the input data, which is this particular one here. It means that its function now is to pre-process our data. And I'm sure in the machine learning, we must have done something that might have maybe shown us a bit about the pre-processing data. It means that we're like getting our data in a way to make sure that it aligns with our predicted output. So that's the beauty behind this perceptron and artificial intelligence with respect to deep learning. So for these optimizers right here, for the optimizers here, we have different optimizers like the gradient descent, the stochastic gradient descent, all these things I will explain it in a moment. We have the mini batch, we have the stochastic gradient descent with momentum, which is actually nice. We have the ADA grad, we have the RMS, PM prop, and we have the Adam optimizers. Now remember that it's not for us to cram this thing, it's for us to just know the exact one to use. So the beauty about coding is whenever you need something, you can always get your template. So you can always get your resources from the internet without having to cram all these things. So, but one thing we also need to understand is when it comes to backpropagation, we are not talking about activation function again. Activation function is for the forward propagation. For the backpropagation, now we're talking about the optimizers. And just like I said, why do we need our optimizer? We need our optimizer to update our weight. And why do we need to update our weight? To make sure that, well, we need to minimize our loss. So that's why we need our optimizers here. So we're running in the backpropagation, we're running the optimizers, we're running the weight updating, and we're running the chain rule of differentiation. So that's the sweet part about perceptron. So all these ones are just to maybe still explain to us the idea behind the weight updation formula, which I just said earlier. And now, if we're running, now please, if maybe you've never heard about epoch before, please let me know, EPOCH. If you've never heard about epoch before, please let me know. But at some point when we are running our CNN, which is the convolutional neural network, dealing with pictures and the likes, I saw epoch and I was like, what is epoch? What is epoch? Now, someone just gave me the simple definition of epoch. Epoch is just the combination of your forward propagation and your backward propagation. So it's more like the forward and the back, like the going front and the back till you get the perfect accuracy. That's what epoch is. So in your perceptron now, when you're done running your forward propagation and your backward propagation, you've gotten one epoch. So now it depends on how many times you have to do your forward and back propagation for you to, like, maybe the more you do your forward and backward propagation, the more you have your epoch and the more you have your accuracy. So epoch simply means the forward and propagation, forward propagation and the back propagation, forward propagation and back propagation. So when we have one forward propagation and one back propagation, then we have one epoch. So epoch is just equal to forward propagation plus back propagation. So that's the idea behind epoch. You don't need to go look for bigger terms. There are no bigger terms. This is just the basic and the fundamentals, and there's nothing much to epoch than just the addition of a forward and a back propagation.
You know, you say
Sorry, Mr. Mufta, are you talking to me? Do you have any questions before I go for that?
Sorry, it was a mistake. I just
Okay,
admitted
no,
myself without knowing.
okay,
Sorry about
no
that.
problem. No problem. You're welcome. So that's the idea behind this. And I'll also give you one side note there. I understand the need to build our stuff. Like when I got this message about taking this class, I was elated, though it was impromptu, but it was okay. So one thing is I had to go to my data set and I started like trying to work on some things. And aside the fact that CNN can eat your data, like CNN lives on data, artificial intelligence lives on data, like not data as per your input, it lives on data bound to like for you to download your dependencies, you have to like get like maybe a particular one with just for a dependency to be installed, you need to maybe have at least a gig for a particular tendency to, a dependency to install. So um, there's something in our systems naturally that we should have, but if we don't have it, it's okay. That's why Google Colab is there. But there's something there, like maybe a dedicated graphics card, and well, because for us to, there is a particular data we have to run, not here, right? Not here per se, but at some point in our life, people might need to like go further and run some data, and we have to like work with so many epochs. Like you have to like do 1,000 epoch. If it's on a system that doesn't have a dedicated graphics card, then it's going to crash. So this is a side note. It's not like I'm saying don't go further, go further, but we just need to understand that there are specifications to like the systems that we use when we want to like go into the advanced phase of convolution neural networks, artificial neural networks, recurrent neural networks, all those kind of terms. I don't want to bore you with those terms, but you need your graphics card, you need your graphics. Like that's the beauty of NVIDIA. NVIDIA now, like they had so much profit last year and last 2 years because of for ChatGPT to run their epochs, they had to get so many they had to get so many RAMs. They had to get so many RAMs from Nvidia, and Nvidia they're like the people selling these things. It's just like this is a gold rush now, and Nvidia they are not even into the gold rush. They are just selling shovels to or hoes or maybe ass to people trying to dig the ground to find. So the ass or the hose they are selling to people is just like in the sense of in the sense of huge RAMs, dedicated graphics card, so that at least your system will be able to run epochs continuously without ever crashing. So that's the beauty about having your dedicated graphics card. So okay, so well, we have our different optimizers, starting from the gradient descent, which is the first one we talked about, and the gradient descent is centered on binary classification, and we have others too. So the disadvantages are listed here. Resource extensive, it needs huge RAM, which is understandable, and we have the stochastic, which is well, it needs a lower random access memory, and the convergence is very slow. Well, I will also explain that particular part. Bear with me. For the mini batch, I will also explain this particular one. Now, the beauty about this SDD with a momentum is, well, it gets you your convergence as fast, like not as fast as possible, but compared to gradient descent and the mini batch or the other one, stochastic and gradient descent without the momentum. This particular one with the momentum is actually way better. It gets you your convergence without creating a lot of noise. Without creating a lot of noise, you just get your convergence way faster. And then we also have this particular one they call ADA grad, and we have the one they call ADA delta, and we have ADAM. Though I'm skipping the others, but this ADAM, the beauty about this Adam, because right now it is the best optimizer. So most of what we are going to be working on is actually going to be like we'll be using our Adam optimizer to get most of what we're working on. And then the beauty about this Adam optimizer here is it's the combination of your stochastic gradient descent with the momentum and your RMS prop. So now if you join all these ones together, you're going to get your Adam optimizer. And then it's very good because now that, just like I said, the other ones will be giving you noise, but this particular one will not give you noise. And if it should give you noise, it should be minimal. So Adam optimizer is going to like have a very, very smoothing effect compared to the noise that the other ones are producing. So for us to reduce the noise, we have to smoothen the edges, and that's what Adam Optimizer is good at. And also our learning rate is going to be very adaptive. But we'll get to the part. I hope you remember the learning rate too. The learning rate I talked about in the weight updating, where if I, like I said, if we have to like use a high learning rate, it overshoots the minimum. But if we use the low one, it doesn't get us our convergence on time. And remember what I said about the convergence. Our convergence is the part where we have our global minimum as fast as possible. Our convergence is the bottom of this. Sorry, let me go to. Our convergence is like this bottom here. So when it gets to this particular one, this is the global minimum, and it's also our convergence. I hope you are, I'm carrying you along. Please walk with me. And so that's the beauty behind all these particular ones. And well, there are more to these particular things, but now that I've talked about the CNN, I also need to also maybe talk about one other part too. So please walk with me. Now I've explained the idea behind the perceptron and everything about the perceptron. Now I also want to explain, maybe when you're running your CNN, which is in your deep learning, there's something they call the input image, because a CNN is all about input. There's something they call the input image in the terms of piezo from 0 to 255. There's something they call the stripes. Sorry if I'm not pronouncing it very well. There's something they call the paddings. There's something they call max pooling, though max pooling is just like a type of pooling. We have max pooling and we have the minimum, we have the max pooling and the mean pooling and the average pooling. So you need to understand the idea, because if we're running our CNN, you need to understand why we are actually doing a max pooling. And we also need to understand why we are padding our data or our image. So all those things, we need to understand them. So I would not want to take our time on this, but I just want us to understand the whole idea. And unfortunately, I might not go so deep into this because I did not have time to really get my notes on this particular stride or this particular mass pooling, but just work with me and hopefully you understand this particular thing. And okay, so now for our input image now, which is in a matrix form, it's like, let's say this particular one now is like 1, 2, 3, 4, 5, 6, 7, 8, which is like in an 8 by 8 matrix form. Our input here now is between ones and zeros. That's if we've done our feature scaling. But if we've not done our feature scaling, it should be between 0 and 255. Now our input here is okay. Now one thing we need to understand is we have our input matrix, and we also have something they call filter or kernels. Filter or kernels. We might see it when we go down, but I just want us to maybe just work with me. Now we have something they call filter or kernels. Now, the idea behind this is when we want to run our input image now, the idea is us getting the necessary features in our image for us to pre-process it in a way that we get us our like accurate output. So what we will do is we'll put our filter. Now let's say this highlighted part now is like the filter. Now we'll put our filter on this particular side. And then if we put our filter here, then we'll work with multiplying the value in the filter with the input. And then when we're done multiplying, then we'll be able to get our output. Now, if we have a 6 by 6 matrix, a 6 by 6 input image, and we pass it through a 3x3 filter, we should naturally get something like a 4x4 output. If we naturally run our multiplications, we should get a 4x4 output. I will explain that in a moment, but the whole concept behind this is when we are multiplying a bigger value with a smaller value, like when we are multiplying a bigger matrix with a smaller matrix, there's all tendency that we get like a smaller output than the bigger input and a bigger output than the filter output that we're actually multiplying it with. I understand that this might be a bit confusing, but the idea behind this kind of multiplication is when we want to multiply, we multiply our inputs with our filter, and then this matrix here, which is like an 8x8 matrix, is like the weight input, and then this highlighted part here is the filter here. And then when we're done, just like you're seeing this particular one now, we have our weight input, but the output is smaller than the input. It means that for this 8x8, now we're getting a 6x6 output. Then for a 6x6 input, naturally we should get a 4x4 output if we're using a 3x3 filter. And the formula behind this is just your number of inputs minus your filter plus 1. And then, so if your input is 6 and your filter is 3x3, then you're going to get 6 minus 3 plus 1, you're going to get 4. Then for this 8, 8 minus, so you're going to get from 8, you're going to get your 6. So that's the beauty behind this. Well, there's a lot of beauty with respect to CNN and AI, but I like saying that's the beauty behind it so that at least we tend to understand. Now, the idea behind this stride now is, stride is nothing much. It's just like we're saying, okay, if our stride now should actually mean anything, then the concept behind the stride is just if we move maybe our multiplication now from this first column now, I will move it to this next one. It means that we've moved our stride by 1. So there's no technical definition behind stride. It just means the rate at which we move our filter on our input system or on our input. So there's nothing much to it. The stride is just like if okay, now that I have my 3x3 now, and I want to maybe calculate the other side, then if I say my stride is 1, it means that I am starting from this second one and I'm moving between the second to the fourth. And then by the time we're done with our calculations, all these parts will be filled up. So that's the idea behind stride. There's nothing to it. There's nothing to it. It's just the rate at which we move our filter from one part of the input system to the other part. So we can actually say, okay, let's do one stride and one stride. We can say, let's do 2 strides. So there's nothing to it. And then another thing here is now that, okay, we've been able to get our outputs now, not like our output, but our output layer. We've been able to see that, okay, the input here is bigger than the output. In a way, in as much as I'm trying to get my information, I'm trying to get the necessary features that will be able to get me what I want in my output, I am losing information. I am losing this, like to an extent, I'm losing some things. I am having what they call information loss. So what do I do to mitigate this effect? Because if I don't do something, I might not really get the information that I want to get at my output. Because right now, I've been able to use a filter of maybe, let's say, 3x3 on an 8x8 input, and I'm getting a 6x6 output. So I have to do something in order for me not to lose as much information that I should. And that's where the idea behind padding comes in. For some of us that might have done HTML and CSS, padding is just when you're designing your stuff, we add external things around us so that we don't, like, let's say if I want to look fat now, all I just have to do is I just have to maybe wear a cloth and pad the cloth so that when someone sees me, they see that, okay, padding is going on. Like maybe I'm fat, but in a way I'm not fat. In a way I'm just padded. So the idea behind this padding is if we have a 6x6 input, and then I run it through a 3x3 filter, and then I'm getting something like a 4x4 output, what do I have to do? The best thing for us to do is by introducing padding. And the padding there is, we're going to, sorry, let me just slide down if I might be able to just see. So the idea behind padding now is, well, this highlighted gray part is the padded side now. Now we've gotten a 6x6 output, but I don't want my information to, I don't want to lose my information. I don't want the parts where my input or my output is much bad than the input. I want something with a higher level of accuracy. So what do? After getting or extracting the necessary features I need for my input, what I need to do is, okay, introduce paddings here. And the reason why we introduce padding is just to not lose our information. So now we've done padding now, and the padding here is this. So now it was 6x6 output, but now we are having an 8x8 we're having an 8x8 output because of we introduced padding at all sites now. So that's one of the beauties. Now you'll be asking that, okay, why do we even need to maybe go through the stress of extracting the information, and then because we don't want to lose information, then we're not padding it? Why not just use the input as the output instead, since the input now is what it is, and then we're trying to make sure that the output is as big as the input. So the idea behind this is, the input, we don't need everything so as to prevent something they call overfitting. We don't need everything. We just need the necessary features. We need something that are like some things that are necessary. So it's just like if I tell you now that, what do you need your leg for? I can list a lot of things, like say, okay, for your leg now, you need your leg for maybe eating. Like you need your leg to carry spoon, you need your leg to walk, you need your leg to jump. Now, if I say, okay, extract the important features for the benefits of your leg, you will take that, like you will extract, we need our legs to walk, and you will also extract, we need our legs to jump. You will not use, we need our legs to eat, because of it is not necessary. Like it is not important to like what we are about to train. So that's why when we're having our inputs here, we are just trying to make sure that we extract the necessary things from our input in order for us to get the output. But because we don't want to lose information in that process, then we have to cover it up with what they call padding, so as not to lose so much information. Please, just like I said, if at any point you need clarifications on this, just let me know. I'll be here to answer your questions. And then with that, we'll have to do our bit updating, and then by the time we're done, with this, we'll come to this part where they call pooling. And then what is pooling? Let me know if there's good definition about pooling. Just like I said, we have 3 types of pooling. We have the mass pooling, we have the mean pooling, and we have the average pooling. Now, what is mass pooling? What is mean pooling? What is average pooling? And why do we need pooling? Now, we just need pooling. Why do we need pooling? So we just need pooling because of, okay, let's say now that we've gotten our inputs based on, after we're done with our party, now that we've gotten our input, what is the best thing to do? We need to extract the best features out of it again. And how do we extract the best features? Or how do we extract just anything that is very necessary to whatever we're trying to train, or whatever we're trying to get? The best way for us to do it is by, okay, so now for mass pooling, now what we'll do naturally is, if at any point we have, now in this particular one now, if at any point we're trying to run something they call mass pooling now, our filters are like, in this particular one, we're differentiating our filters with maybe, let's say, these different colors here. Now, so for this particular filter here, the max pooling is 6. It means that we're extracting the feature with the highest data. That is it. Like we're extracting the feature with the highest data. So that's max pooling. It's looking for the max in each feature, in each filter, and it's extracting it into this particular one, thereby downsizing it or downsampling, but that's not the point. The point is when it comes to max pooling, which is very necessary in order for us to extract what we need to extract, we look for the highest value in the features and then we extract it. Remember, this is a filter on its own, filter or kernel. This is a filter on its own. So we will be looking for the highest one between this particular filter. What is the highest one? The highest one is 6, and that's why we have 6 here. And then in this particular one, because of now, when it comes to max pooling, it always works with a stride of 2. So we're like moving 1, 2, and going to this particular one. So when it comes to this one, our highest feature here is 8. So that's why we have our 8 here. And when it comes to this one, our highest is 3. And that's why we have our 3 here. And when it also comes to this one, our highest is 4. And that's why we have 4 here. But if it's about mean pooling, we are not looking for the highest feature. We are looking for the lowest feature. So if it's mean pooling, I will just use 1 here. We'll use 2 here. We'll use 1 here. And we'll use 0 here for our mean pooling. And for our average pooling, we know what average is now, the summation of all the whole features divided by the number of those features. So that's how we run it when it comes to convolution neural networks. And then, well, it's not just enough just to do your pooling or your max mean pooling or your average pooling. It's not just enough. So we have to do something they call flattening. So the flattening here is, let me not go deep. The flattening here is, this is a 2D image now, but for us to pass it through so that it goes to the output, we have to turn it to a 1D image. And how do we turn a 2D image or flatten a 2D image to a 1? We just have to, let's say we'll now make this particular one long. So meaning that we'll have 1 column and 4 rows. So we'll not have 2 rows and 2 columns again. When we want to flatten something, we can just make it 1 column. Like when we want to flatten, it has to be 1 column and maybe any amount of rows based on the input we have after our max pooling or after our pooling. So it's going to be 6, 3, 8, 4. And then when we are done with our flattening, then we push it to the output layer. So that's the whole idea behind and convolution neural network operations. So I'm not sure there's any tangible thing here, except, okay, this particular one now, we have our first sample, which is the input. And then we have to pass our filter through it. And then by the time we're done passing our filter through it, then we'll be able to get our input here. But our input is not enough. We have to make sure that we stop any information loss. So we have to pad it. And then we'll now continue the passing of the filter again. And then when we're done with our passing of the filter, at some point we'll do our max pooling, because our max pooling is the most acceptable one. And then when we're done with our max pooling, then this long thing you're seeing here is when we now flattened the outcome of our max pooling. So, well, this is the flattening effect, and then it's moving to the output. So there are different illustrations to explain this particular thing, and there's just so much to do, but this particular thing should not just confuse you. This is just the whole concept behind this. We'll have our input, to pass our input through our filter, and then our filter, based on maybe the input is bigger than the filter, then we'll get our output, which is smaller. And to reduce information loss, we have to pad it. And then we'll run our filtering again. And then when we're done with our filtering, and then we'll then do max pooling. And then when we're done with our max pooling, just to extract the the most important ones, most important feature, then we're going to flatten it, pass it through the output, and then we're going to get our output. So that's like the fundamentals with respect to what I will be talking about on UNet. But please, does anyone have any question before I move to the next one as fast as possible? Does anyone have any question, please? Does anyone have any question, or should I move along?
Hello, Mr. Obinna.
Okay. Thank you,
Good.
Mr. So,
Yes. Good afternoon. Yeah, I think you said it. You said a lot. You said a lot, and honestly, I had question at the beginning just about when you started. But right now, if I have to continue asking my question, you will have to go over your course. I wanted to actually ask then, if for you that to differentiate between bias and weight, because when you started, I like the analogy you were giving. You were very relatable, but along the line, I think I understood it. Yeah, somebody also dropped in the chat box, how materials where we can do further study, because these things are quite I think they are technical. They are quite technical. Yeah, that's more like a comment for me. Thank you.
okay. Let me use this particular term again let me use this particular term for our weights now. Just like I said earlier, our weights are more like the level of importance we give to a particular input. Now, I use the eye and the skin. You won't allow someone's hand get close to your eye, but you don't mind the person tapping your skin, like tapping your hand. Well, it's your skin, but you won't really mind. But you remind the person tapping your eye. So if we should actually say the input, now the input, we understand it. Like, let's say the eyes, the skin, they are processing data. When the skin touches something that is hot, it will process the data that it is hot, and it will not touch it again, just like a kid trying out something for the first time, touches something hot. Nobody will tell him or her not to touch it again. So our skin, our body system, we're always processing data. Now, when it comes to the weight, now it is the level of importance we give to a particular input. Now, for your eye, just like I said, you won't want someone touching your eye, but you don't mind the person touching your hand. So that's the level of importance we give to it. Sorry, but did I answer your question, or should I maybe use other
Yeah,
analogies?
yes, I understand. I understand the weight.
Okay, and the
The weight.
bias now, the bias,
Yes, the bias.
the,
Yes.
the bias here is okay. Now, our body naturally, we need to process information. We need to process information. Like, we have to process information. But there are some times that naturally you now, even though you have all your sense organs and they are working, you just want to rest. There's this initial you have, this reluctance that you have to do stuffs. You really don't want to do stuffs because of you just need to rest. But let's say you're lying down on on your bed, you want to rest. You've had a busy week, and then you like maybe like maybe a breakable plate is at the edge of your table, and in a way it's slanted, and you're looking at this thing, you're telling yourself that this will fall down, but you're too tired, you don't want to process this thing, but you're looking at it, it will fall down. And then slowly by gently, it's like sliding. So naturally now the bias there is, in as much as your body wants dormancy, doesn't really want to do anything, the bias there is trying to convert that inactivity or passivity. It's trying to convert it to an activity. So it will naturally just make sure that you process an information as fast as possible and make sure that, okay, your body or whatever you're sending to the brain is not zero. Okay, so normally what bias is, the idea is like it shifts our decision boundary away from origin. And what does it mean? It means that it makes sure that whatever we process, even though we don't want to process anything, but whatever passes through our neurons is not zero. That it in a bias process, meaning that even if you just want to sleep, your brain will just, though your weight is 0, you're telling yourself you don't want to process, your brain will naturally tell your decision that, okay, I must take this guy away from 0 and process anything that is entering the neurons, process it into 1, so that at least your brain is like, so that's the whole idea behind the bias, making sure that our zeros, in case of our inactivity, are not passed through the neurons as zeros. It is passed through the neurons as 1. So it is converting every zeros in case of their zeros in our days of inactivity. It is converting everything to 1 before it is being passed to other parts of our perceptions. So I don't know if you understand this.
Yes, I do. Thank you, sir.
Thank you very much. Okay, so we'll just if in case of maybe other questions, please let me know. I'll be here to answer your questions. And I'm sorry, I should have introduced my colleague Naomi to this. I was so keen on, but that's okay. Naomi, you're highly welcome. Okay, so now we'll be talking about units. We'll be talking about semantic segmentations, and we'll also be talking about object detection. Now, I don't want to bore us with what is a unit, what is semantic, and what is but we just need to, okay, what is unit as per maybe my own definition? Unit is just more like a convolution neural network architecture. There's nothing more to it. But the beauty behind units is it's like very, very helpful when we're trying to find out a particular thing. In like, okay, let me use this term, medical analysis now. When because of we need this particular deep learning terms in the lines of medicine. So the medical staffs, based on they don't have plenty data, they had to come up with a term or with a particular model that with the little data it has, it's just going to process the data in a way that if maybe they're looking for a tumor in the head and upon our normal eyes, we're not able to see the tumor, a particular model, a particular architecture will be able to like look at the tumor and be able to like extract the features, locate the tumor and the dimensions of that tumor beyond our natural eyes and beyond the IL, beyond whatever X-ray can get us. So that's the idea behind the unit. It's helping us maybe find out a lot of things that naturally we should not find. It's like a fully convolutional neural network that is designed to learn from a fewer training sample. So I just please, I don't know where I might have kept my unit diagram, but just please bear with me while I try maybe get the diagram, because of from the diagram I should be able to explain this thing more. Okay, sorry. Let me just go to images here. Okay, so this is our unit. So it's called unit because of it's in a U shape. It's in a U shape. So okay, just a minute. Trying to expand it, but let me not bore you guys with this particular thing. The internet might really not get us what we want. Just need to get something of this. Okay, not really getting it, but I'm just trying to get us this unit. Just give me a minute. Let me find it out. I thought I might have gotten it, but okay, sorry. Okay, so okay, I had it opened already, so I won't be reading about the whole unit, blah, 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 but I just want us to get the diagram from here now. Now, this is unit architecture. It's called unit because of it's in a U shape. So what better way to get our name than using the unit from the shape? Now the idea is it comprises of different blocks, well, and it's also like separated into the encoding part and the decoding part. The encoding extracts information that we should use, and then the decoding part actually gets the information. So it's more like we're downsizing, and then we're now upsampling. So on the left-hand side of the diagram, there are 4 encoder blocks, and on the right-hand side, there are also 4 decoder blocks. One of the main features of the unit is the encoder-decoder structure, which is on the left-hand and the right-hand side. Now, it's not just for me to just tell you this is structure, this is the reason why we have this particular unit here is because it is it was founded in 2015, I think, and it was able to get very important features that naturally we are not gotten from other architecture and CNN architectures. The unit got it. So that's why it's something that even tonight it's actually very good. Though we also have maybe others like the fast CNN, the RCNN and the rest, but unit still, to an extent, when it comes to the biological line, is very good. It's very helpful in finding out some more. I'll show you 1 or 2 codes on it. But I just want to like rush this particular one. So like I said, on the left-hand side, so first, the encoder receives the input image, then extracts useful. Please remember, I'll be saying these particular things, and I want us to relate it to my explanation of the CNN. So that's why we had to go back to that particular thing. So now, for this particular side, the encoder receives the input image now, and then extract useful features from the image using multiple convolution layers. Like these are the multiple convolution layers. And then the decoder then upsamples the features using transpose convolution. Transpose convolution is more like the opposite of the downsizing or the downsampling that we actually used initially. And then for this particular side, a concatenation is happening because of while it is trying to upsample it, it is better to just take shortcuts to an extent for some people. They like taking shortcuts. So what they would naturally do is, since this particular side has been trained already, how about we just get the important features from this particular side and add it to our output? So in a way, for them to get this particular side, which is the right-hand side, our decoder block, they can actually just concatenate with the input and get like important parts of the features and then use it. So this particular one is actually beautiful. And well, just like I said, the decoder then upsamples the features using transpose convolution and concatenates them with the process called skip connection. So in as much as we're having our concatenation here, there's something they call skip connection, and I'll explain it in a minute. So the idea behind this is in order to produce a result that looks like a segmentation marks output from the network, I will show you what a semantic segmentation marks looks like. And when you see the marks, you'll be able to understand that, oh, well, this is the only way a tumor can be detected when it comes to CNN. So, and another important feature of this unit is the skip connection. Now, skip connection, like the name implies, it skips some of the layer in the neural, like this is the skip connection. I'm sorry, it was not labeled here. This is the skip connection. Now, the skip connection skips some of these layers now in the neural network and feeds the output of one layer. Like it feeds this output now of one layer. Like so that's what I said earlier, that it's light shortcut. So most times it will just say, okay, instead of stressing itself, training itself, how about you get the important features that was trained in the this particular one, which is the encoded blocks, and then skip it and use it to this side. I'll use it in this side. So that's the beauty. It skips it, and after skipping it, it feeds the output of one layer as the input to the next layer. So if you look closer, you will see the arrows representing the skip, like these arrows now, you will see it representing the skip connection process. This process helps to transfer the selected feature directly from the encoder to the decoder. So this is the encoder. Now it's transferring the selected feature from this encoder now to this decoder part of the network, which as a result helps the decoder to this unit. It is very necessary for semantic segmentation. And why do we need our semantic segmentation? Please confirm if you can hear me. I'm seeing my internet is unstable. Please confirm if I'm audible.
Yeah, you went off for half a second, but we can hear you now.
Okay, thank you. So that's the idea behind units. And well, the unit is mostly used in the medical line in order for us to mark some any issues that has to be marked and find the exact dimension of that particular issue. So that's it. So going down here, this is the code with respect to how unit is implemented. This particular thing now is just the same thing. Like whatever we see here, now we're not implementing it now. But before we go to this particular one, I will show you what it looks like in a code that was generated by our team at Transformational College. And then we'll be able to, all these ones are just the textbook definition, but this thing is so factual, it's correct, meaning that it started from this first encoder block to this last output segmentation map. So that is it. And we also need to remember with respect to this unit, in the encoder, we're encoding our layers, and then we're not downsampling. And then in the process of downsampling, there's this thing we also need, which is the max pooling. So if you're seeing this red thing here, it means that we're max pooling every layer that we are downsampling. But max pooling the layer, and then we'll max pool this one too. And then after max pooling, we're max pooling this one, we're max pooling this one. And then after that, we'll come into this part where we'll have to go to the decoder part. Now for the decoder part, because we don't want to lose as much information that will be detrimental to our output. So what we need to do is we need to upsample it. So now for this encoding that uses a max pooling feature now, for the decoding, what we'll be using when it comes to unit architecture is the transpose convolution. And then naturally, when it comes to this particular part, just like you're seeing here, it is unpadded, but in this particular one, while we are trying to upsample it, we're padding it. So all these things are just talks. I'll show you the code. But if you have any questions with respect to this unit, please let me know. I'll be like happy to answer your questions before we go to the code part. Disclaimer here, the code will not be run, like we will not run any code from scratch because it has been done before. Just like I said, the running of these codes are expensive, the downloading of dependencies, and I don't want that part where I have to download dependencies again and maybe engage in any runtime that will exceed 30 minutes beyond this particular time, and then maybe affects my network where I have to be logged out because of one thing or the other. So that's why we had to run this thing at the backstage, but you're going to see the input and you're also going to see the output. So now, with respect to this, we'll go to, before we go to the next one, please, which IDE have you been using so far? Because I don't know if you know Jupyter Notebook, but I heard you guys have been using the VS Code and maybe the Google Colab. Please, can you confirm that?
Yes, we
Hello.
are familiar with VS Code, Jupyter Notebook, and Google Colab, but we practically use VS Code and Google Colab in our classes.
Okay. Well, today I'll be showing you this stuff on Jupyter Notebook, and maybe you need to go online and check possible IDEs to use to use, like environments and systems to use when it comes to this particular thing. But the beauty behind Jupyter Notebook is, or the beauty behind Google Colab is, whatever works on Jupyter Notebook also works on Google Colab, meaning that just like we have TST as like the file formats of Word file, we have IPYNB as the file format of Jupyter Notebook, which can also be opened on Google Colab. So that's the beauty behind this particular thing. And I'll just show you the codes, and then we'll just scan through the codes. And some point I would have shown you CNNs and the rest, but well, time has gone. But if you're seeing this epoch here, just like I said, epoch is the combination of your forward propagation and your back propagation. And now this epoch was trained in a way that it's going to it's going to have a forward and back propagation 50 times. That's why you're seeing this. So when you're seeing one epoch, it means that it has gone front and back one up to the 50th time. So that's the idea behind the epoch. And for this semantic segmentation, this is the code behind it. We had to install our dependencies and our modules. All these things were expensive, but it's something we're happy to do. And now, based on the marks I talked about earlier, now if you look at this is what the input looks like. If we use our matplotlib or our plotly, this is what our input looks like. But after we're done with this particular thing, it's now generating this output, making it look like a masked object. So it has to pass through the units. It has to pass through the unit architecture for it to get this particular one. So we could actually go further, but please don't see this code as something that will derail you. It's something that naturally you will love if maybe you give it a try. I'm sure you will love it. Now, if you look at this particular thing here, you're going to see dropout, you're going to see max pooling. All these things are just a code representation of what we have in our graphical term. Now, I did not explain this dropout. I'm sorry, but this dropout is just in a way to prevent overfitting. And why do we need dropout in our neural network? The dropout means that neural network naturally has this tendency of depending on certain features or certain training data. And it's not really good because of, in a way, when it depends on certain things or certain training data, we tend to get high training accuracy. But when it comes to showing results, then we'll now get low test accuracy, and this is not good. So what dropout means is it looks at the neurons or the training data that has a 50% probability, and then it drops it. It takes it out. It randomly drops those neurons, and then after dropping the neuron, the ones that are still available will become more active. It's just like in a work environment now, to reduce the level of redundancy in a workforce. You look at the people that are responsible for those redundancies and then you take them away. And then when they see that there's a downsizing in the organization, those ones that are still available will now buckle up and try to make sure that they don't lose their position. So that's the idea behind dropout when it comes to CNN. In order for us to reduce any amount of dependencies in our neurons, what we just do is we make sure that we drop out something. So that's why we are seeing this dropout here, because of we are having a lot of files here, and in a way it's going to create overfitting. So that's why we have a dropout here. So, but that's not the point, but I just had to explain it. And that's the beauty behind CNN and understanding the fundamentals behind CNN. When we see it in codes, we understand what everything means. And when we write it, we understand what we are writing. We don't just write anything, we understand what we are writing. So this is another particular one. And then the output of our unit is getting us this max shape. So that's the beauty of our unit. In a way, it's getting us things that naturally we won't get if we maybe use our normal approach. So you will get your input here, and after running your unit architecture, following all due process, then you will get your output here. So our output for this one is this. So that's what we got when we had to run this thing in. Just like I said, it's not cheap, but it's fixable. And then one thing again here is when we check our inputs and our outputs here, we also check our loss function, which is the comparison between the predicted and the real one. And then when we're done, we'll be able to get whether they are correlated. All these things you're seeing here is what they call noise. And that's why we need our optimizer in order for us to get what we need to get. And so we did another one again where we had to run a road scene semantic segmentation using our unit again. And then this is what we did. So you need to understand that we've put a lot of work into this particular one. And you need to also know that it's because of we see this particular, should I say, this lecture or these particular meetings, we see it as very, very important to your foundational knowledge when it comes to your artificial intelligence goal. So we have to make sure that we get everything you want. And if in a way you want all these codes, we can give it to you. So that's no problem. So this is like the input and this is the output. And the idea behind this is for us to get our masked shape using our unit architecture. So this is what the unit looks like, just like I showed you in that textbook. This is what the unit looks like. And we follow all the right approach, but also going to get this particular approach. And then now, just like you're seeing, we're seeing the masked part, which is the most important one. I will also show you the parts of the brain tumor, which is also very, very necessary. So all these ones are, when we're done, we'll also have to compare and combine in order for us to get our loss or try to make sure that our loss is not so much. So that is it. So all these ones now are also the inputs and the outputs. So I want us to understand that as long as we have our architecture intact, the unit is just a go-to place when it comes to finding our inputs and our outputs. So let me not just go and maybe waste your time. Now, this is the one we did for the brain tumor now. So just like we said, we got our dependencies and we did everything. And then look at this particular one now. Remember, I said when it comes to units, it works with less data. It doesn't really it doesn't really need as much data as it should, because when you're trying to treat yourself, how many data do you need to generate before you get what you need? Medical lines don't really have a lot of data because of, well, if they have to snap someone's brain, how many times do they have to snap it for them to generate what they need? So unit is the go-to part or go-to architecture when it comes to generating data with less input. So now for this magnetic resonance indicator, if I remember my physics very well, this is the image that was generated. Now, if you pass it through the unit architecture, you're going to see this particular one. Now, anybody in medical line, when they look at this particular one, now they'll be able to know that, okay, this was extracted using the unit, and looking at this particular one now, they should be able to know if this is the size of the tumor when it comes to how they should allocate their treatments or their medication. So that's the beauty behind this um, um, units and semantic segmentation. So the idea here is what we have here is what they call semantic segmentation, meaning that if I have to explain semantic segmentation, I'll say it is a procedure where where something specific on a picture, like maybe a brain tumor, just like we're seeing here. But we're also able to create a max, which is this particular one here, to show where that particular, maybe let's say the tumor is, and also to specify where it is located and also give its dimensions. So that's the idea behind semantic segmentation and having the unit architecture run the semantic segmentation for us. Please remember, if you have any question, let me know. Rounding up very soon, but let me know if you have. So now this is the part where we had to define it. But after defining, one thing about Jupyter Notebook is the each cell is not dependent on the previous cell. So as long as you've done one particular thing here, you can go up and should I say update the cells that are on top. So it's not really dependent on each cell, just like Google Colab. So these are the things we're talking about. We have our input layer, we have our dropout, we have our max pooling, we have our dropout. Just like I said with our dropout, we have our concatenate. And remember, our concatenate is just like the skip function where we are taking features from the encoded parts. I was moving it, concatenating it to the decoded parts. So that's why we're having our concatenate here and our dropout here, our concatenate. So all these things are terms that would naturally we follow. So that's the beauty of this particular one. And we did a lot. It's just we could not maybe do as much because of the time factor. It's not something I want to write because I'm sure if I was writing it from the scratch in this particular thing, it would take a lot of time. And just imagine I'm writing words that you're not really accustomed with. You will get bored and I don't want to lose you. So that's why. So that's just about it for um, UNet and semantic segmentation. Remember that semantic segmentation, it is not only predicting where something is, like where something specific is on a picture, just like that brain tumor I showed you, but it is also like able to create a max, just like that picture too. And it is using that max to show where on the image that specific tumor is located and also giving its dimension. So that's what semantic segmentation is. Like it is just creating a max, showing us that in as much as your eye can't see it, I will show you where it is by creating a max so that with the size and the dimension, you should know if it's a big tumor, God forbid, or it is if the tumor is malignant or it is something that we just maybe it's inconsequential, something. So that's the beauty behind using UNet to work on our semantic segmentation. Now, this object detection, because I just wanted us to go back to like the fundamentals and the basics, and then come back to our semantic segmentation, the UNet, which is the bone of contention of our today's discussion, and also round it up with our object detection. But I won't work with this particular one, but this one is just to, like this particular one is trained, and so I won't work with this particular one because you might not really understand it. I will work on this particular one that is here, this particular one. Now the object detection now. Let's say just like a kid now, you're trying to train a kid how to locate or how to be able to differentiate between sweet and between sweet and between something sweet and something that is not sweet, or between a sweet and between something that is bitter. Now let's say your kid now, the first time they touch a sweet with their tongue, as per the inputs now, one of our sense organs, as per our tongue now, when they touch it, their eye will go up. The first time my nephew touched, I took him to Cold Stone and I bought sweets. I was the first to buy him ice cream. He was very young then. I bought him ice cream and the first time he licked the ice cream, like the way his eye brightened up, like wow, this is heaven on earth. Is this how heaven is or something like that? Like, I got that feeling that, well, if my boy was a model, I was able to train him very well for him to know that, okay, ice cream is sweet. And then there was a particular time he fell sick and he had to take malaria drug. Well, I'm not sure. I think the one we gave him was not as sweet as the previous one someone around me used that was actually a child. But when he licked it, telling him that, "Ah, guy, this particular thing, don't touch it again. It is bitter. And oh, this particular ice cream, it is sweet." So that's one thing about labeling. And why am I talking about this labeling? I'm talking about this labeling because if I want to dictate any object, it means I have to label my model. I have to label my model with a lot of previous related features. Like when I label my model with a lot of previous related features, then I'll be able to like train it or predict future occurrences. Like I did not need more than one ice cream for my boy to understand that ice cream is sweet. And I'm sure if we go to Cold Stone the next time,
We are so sorry. I think Mr. Obinna's network actually tripped. So
sorry,
let's
can
give
you
him.
hear me now?
Oh, okay, all right. We can hear you.
God, my network. I'm sorry. I please indulge me. I'll be done in no time. I just want you to understand the idea behind object detection. Please, okay, let me just not recap, but let me just give you the idea again. Like based on how I trained my boy, it's not like I trained him on how to know that ice cream is sweet. I just had to take him out on a treat, and he licked ice cream and he loved it. And if we go again, because in a way I've trained him, so if we have to go again, he's not going to need
Um,
me to train him.
Sorry, Mr. Obinna, we can't see your screen. Please, if you
Oh,
can
sorry,
share.
sorry. I Okay, so I don't need to tell my boy to go like to all he has to do is if he sees the ice cream banner on our entrance to Cold Stone, he's going to be like, Uncle, I want ice cream. And you know that the reason why he wants ice cream is like the bliss he felt, the sweetness of the ice cream and the creamy taste of the ice cream. Now I've been able to train my boy to understand that okay, ice cream is sweet and malaria drug is bitter. So that's one thing about object detection. When it comes to object detection now, if we have our model, we train our model in a way that whenever it's able to predict or mimic the human ability to think. So if I train my object with so much data, like I like labeled data, I train with so much data, all it has to do is maybe if I just maybe pass an input to it again, and I tell it that, okay, what is this? It is going to tell me that this is a car. So this picture you're seeing now is just maybe this model was trained in a way to just identify different makes of cars. First of all, it's going to identify cars. There are models we have to train in order to identify human beings too. So it depends on what you want to train, and there are different architectures to use in order to train. You can use our like you only look once, which is like the YOLO. We can use maybe the V8 because that's what we used here. We can use different parts. I can't remember other parts because I was also like keen on using this particular one alone. But there are different models we can use in order to train it. For this particular one, we had to use like start this one while using the YOLO, which is like a major dependency. We have to like start from the scratch. So this is just what we generated, which is more like an explanation. So if you want this as a notebook, it will be given to you. But please remember that our models can only predict something if we've passed enough features or if we've passed enough inputs that are related to what we want it to predict. Now, if you want your model now to be able to like detect a particular object, and we've never passed that object to that our model at any point, it will not be able to detect that object. So if you now, you're in your house and you like pass your scan, this is on our phones too. Like there's a feature on my phone where I have to like scan a particular, I have to scan my room. And if I have to pass it through, is it Google Lens or something like that? It is going to tell me everything that it is seen in my room. It is going to tell me. Like there's like Google Lens, yes, it has that kind of model too, where if I need the make of a particular object now, and I need it to tell me the meaning of that, the name of that particular object, not like the name per se, like Givenchy or whatever. Maybe I need it to tell me whether it's a cat or a dog. And I just have to like go through Google Lens and snap that picture, pass it through Google Lens, Google Lens will just tell me that, okay, this is, maybe it's an animal I don't really know about. It's going to tell me that it's a human bird, or it's a raven, or it's a hawk. So the only reason it can tell me, the only reason it can detect such objects is because of it has gone through the phase of being trained consistently with similar objects. So that's the idea behind object detection, training your model with similar objects. When you train your model with similar objects, then when you're not training it again based on what you've used before, it can be able to predict that, hello, sir, what you're showing me now, based on my detection, it is a car, or it is a raven bird, or it is a hawk, or it is an eagle, because it has been trained before. Now, you're not predicting based on the previous trained document. So before we do those particular training, we have to label our data. And that's where, maybe if you're seeing object detection, you're going to see labels. And that's where labeling comes in. So that being said, all these particular ones are just maybe things we use to train. We want to train our car. So when we pass all these things, we'll be able to, like, the car, our models will be able to tell us that, okay, this is a car, this is a truck, these are humans, or person one, person two, person three. And so just like you're seeing here, this is a truck, like based on, it was trained with a lot of labels, which are like the input data. Whenever it shows this particular thing, we're seeing that, okay, this is a truck, and it's giving the truck accuracy of 0.47 with a precision of 0.37, which is not good enough. But to an extent, we know that, okay, it got the name right. It is a truck. And then this one is a bus, which with an accuracy of 0.93 and a precision of 0.73. So all these things are possible because of they were trained previously with similar labels. So that's the whole idea behind object detection. So all these things we're seeing here are because of all these codes that were written here with using our YOLO, you only live once dependency. It's a funny name, but you only live once. That's the dependency here. So it's been able to predict that this is a bus. This one now is been able to predict that this is a motorcycle. And for it to predict, it means that it is noticing, it is detecting the object. So that's why we have our object detection, and it's still part of our convolutional neural networks, which is still part of our deep learning, which is still part of our artificial intelligence. So I'll just be scanning through. This one, it's still able to predict that this is a truck. This one, it is still able to predict that this is a truck, and these are persons because of similar labels we are passed in when we are training the data. So imagine the graphics card we had to use and the loads of dependency, God, this was more, at least this is the outcome, motorcycle. Most times they are not always right. That's why we have to run a forward propagation and a back propagation to make sure that we get everything we want to get. So now, if you can see this one now, you're seeing suitcase. We know that this is not suitcase. Unfortunately, shame on me. I don't know what this is, but I know it is not a suitcase. And I know this side is not a motorcycle. And we know that this side might not be a person. So it is not always right. That's why we have to make sure that our loss function is not as much as it should be. That's why whenever we're running our back propagation, we have to use our optimizer in order to reduce the noise. So now this is sweet because I'm saying terms with words I actually used in explaining earlier. That's the beauty. Saying words, and if I say those words, you understand those words because of it's something you can relate to based on previous explanations. So this is it. It's not always perfect, but well, it can get you the job. Sometimes it gets you the right thing model enough. So it is much, it is much. All these things are just it. It was a long task to do, but it was worth it. So please, does anyone have any question with respect to this before I round this thing up with what I think maybe if you really want to like maybe that's what you also want from me. Does anyone have any question, please?
Hello, sir.
Hello, I can hear you.
All right, thank you very much, sir, for the lecture. This is a lot for one class, actually. I mean to ask, between PyTorch and TensorFlow, is there kind of preference or
Between what?
PyTorch and TensorFlow? Is there kind of preference or which one is more suitable in handling object detection?
Okay. One thing about Python and one thing about PyTorch and TensorFlow is PyTorch now is one of them is owned by Facebook and the other is owned by Google. So they all come with their own different functionality. A lot of people prefer PyTorch and some other people prefer TensorFlow. And now that Microsoft is bringing out its head with their own Azure packages, so it depends on the exact stuff. Now, for me, now if I feel that whatever I need, I'm not getting enough accuracy with what I need, I can decide that okay, I want to use either of them. So it depends on what you want. A lot of people use TensorFlow. Some other people use PyTorch. Like me, I use TensorFlow because TensorFlow is it's bliss in a way because with TensorFlow, the fact that TensorFlow has to they had to buy the Keras and dependency, and then you don't have to install those dependencies differently. That's one beauty I love about TensorFlow. So you can use TensorFlow. Why some other person can say, okay, you know what, I prefer maybe I prefer PyTorch, and they can use PyTorch. It depends on your preference, actually. Depends on your preference. But I would just say when it comes to getting your solution, look for the exact one that you feel is closest to your solution and then use it. So it's good to be versatile in everything you're doing, actually. So I don't know if I answered your question.
Yes, thank you. Please,
Okay,
sir,
please.
we need all the
Okay.
materials so that we can consume them on our own end.
Okay. Okay, no problem. Does anyone have any other question before I go to maybe the roadmap in case maybe you need the roadmap too? Any other question? Okay, so Naomi is here. That's nice. So sorry, Naomi is like my colleague here, and she's as good as I am in this particular stuff. It's just that she just told me to take handle this stuff. Naomi is very, very welcome here, and she's like my esteemed colleague here. So let me just go to the roadmap. I'm happy we all understand this particular thing. So sorry, I need to, okay, this is the roadmap. So for your AI engineering roadmap, for us, for you guys, for everyone that is like you want your AI roadmap, there are things you need to know. You need to know your Python programming. You need to know your statistics. So, because when I talked about probability, when it comes with respect to your dropout, I'm not sure a lot of people understood the idea or the concept behind probability. Probability is very, very important with respect to what we are doing in AI. And then you also need to go to your database, to the database, because when we're like trying to deploy our artificial intelligence model, we need a database to store this data. So, well, the database is important, and then your machine learning is also very, very important because how do we predict our data without machine learning? So we need our machine learning too, and we also need this deep learning that we just talked about, and we need our natural language processing because I talked about um, YouTube at some point, talked about cosine similarities and talked about how our algorithms are so aligned in a way based on what we like and what we say or what we ask prompts our Google search. So this is where NLP, natural language processing, is very, very important. We need it too. And then going further, our machine learning operations, which is the ML ops, we also need it too. So, well, so I'm just saying this because at some point in our life, we tend to like run introspect, like we have our self introspection where we are enthusiastic about AI and we want to make sure that okay, where we started is not where we are based on how we've been checking ourselves so far. So I want you to know that the best way for you to get this thing done, in as much as we're following the what we've done so far, we need to also know that there are things you need to know very well. Like you need to know it. They are non-negotiable. You need to know it. If you're following the technical phase of AI, you need to know those things. So these are the things you need to know. And then if maybe you have any problems with, well, these particular things, like you need help with your Python programming language or your statistics or your feature scaling. I'm sorry, I did not say that feature scaling, where based on we are trying to reduce overfitting now, we need to make sure that, okay, our thing, our data is machine readable. Then we have to feature scale it. Maybe we have to use our standard scaler or our minimal scaler. Standard scaler is between the -3 to 3, and the minimal scaler is between 0 and 1. So all these things, -1 and 1, all these things are very, very important things we need to know. They are non-negotiable, but the good thing is Transformational College is here for you to make sure that, okay, we are going to hold your hand. Any question you have to ask, just meet us. I will help you with the question. So I don't know. Do you have any question before I hand over to um, um, our moderators? Do we have any question, please? Do we have any questions, please? Mr. Olua, Toby, who else? Do we have any questions, please? Okay, so in the absence of any question, if at any point you, because I'm really not on Telegram, but if at any point you really want to reach me, you can send me an invite on my LinkedIn and maybe send a prompt, and then I'll be able to help. But aside that, thanks, or thank you all for indulging me while I go through all these things with you. Hopefully, you're way better than I met you at the beginning of the class. And just like I said, if you need any help, you can reach me out on my LinkedIn. Okay, so thank you, Transformational College. I will be bowing out or muting myself now. Thank you.
All right. Thank you so much, Mr. Thank you so much, Mr. Obinna. It was really insightful. It was a great session. So as a tradition, please, a feedback form has been posted on the chat box. Please, let's all take a minute or less than a minute to fill that up. And while we're also filling that, displaying on my screen, I hope you can all see my screen. I mentioned this at the beginning of the class. I'm going to mention it again. This is a 10 weeks summer program. 10 weeks AI, artificial intelligence and machine learning summer program. We started on the 14th of June, and so far we have not gone too deep into it, and we're hoping to have you all on that program. It's really, really great. It's really, really insightful. So far, we have had 2 classes and it has been wonderful. We have testimonies from people that have taken the class. So I'll be posting the registration link again right now on the chat. Please, let's all do well to register for the program. It's mandatory for us to be on that program. So we can all check the chat box now. The registration link is there and the feedback form is there. So if you have any more questions, if you have things you need to know, you need to ask, you can contact the college admin. A number is being posted on the group chat right now. Your questions, let it be directed to her. Anything you need to know about our programs, anything you need to know about this program, please do well to ask and confirm and get information from the college admin. Please, let's chat done in the chat box when you're done filling the feedback form, please. It will take less than a minute. Please, when you're done filling the feedback form, just chat done in the chat box. So the summer program, as said, it's not mandatory, but it's optional. But it's really necessary if you need to develop yourself in AI and machine learning. I'm waiting for a response in the chat room. When you're done filling the feedback form, please just chat done. All right, thank you, Ode. I need more people. Please chat done after filling up the feedback form.